Welcome to the fascinating world of traffic signals. Today I have a super thanks from Sam, and he asked if I could make a more in-depth video about how these traffic signal controller cabinets work and how they get power to all these lights out in the field. So let's go ahead and open up this traffic signal controller cabinet, and let's get a lot more detailed into how everything in this cabinet works to run a full operation of an intersection. So in Mississippi, we typically see TS1 style cabinets, which this one is. It's kind of a hybrid is what I like to call it, because we do use TS2 options and BIUs for communications with our detections, even with our conflict monitor on a lot of these new cabinets. But then your pedestrian devices are going to be TS1 and hardwired into the backboards. Same with your Opticoms. Same with all of your controller inputs and outputs. They are still hardwired into the backboard here. And this backboard, we're gonna get a lot more detailed into it in a second. I'm gonna pull out the plans and I'll go over some of the key items to it and what makes everything work, what makes this go from the controller down to these load switches, to tell these load switches to go from green to yellow to red, and red to green on particular phases when they need to, as this controller outputs. So let me pull the plans out and we will look into what's making all this work. All right guys, so I have the plans out right here, and these are the plans for the backboard and all of the pin connectors. All of these pin connectors that are going inside, besides this one's not on that sheet of plans. I'll show you a different sheet with that one. But these 3 pin connectors and these 2 pin connectors going into the conflict monitor, that is what's showing, and the entire backboard. That is what all this is showing. These are our pin connectors and our layouts for them, and that's going to go certain pins on this backboard. Those pin connectors are back here behind the backboard itself, and they're soldered to pins that are all of these guys here, and they're jumping into the connectors themselves, routing up and connecting into the controllers, and then it's going to use a low voltage or a ground to communicate from the controller itself to the load switches on which lights need to go from green to yellow to red, which lights need to go from red to green, and it's going to just use that low voltage to make all that happen. And then it will output a 120 volts to signal heads out in the field. Let's keep looking into it real quick. So inside of this cabinet, we are going to have 2 separate types of circuits. We're going to have a flash circuit, and then we're going to have a normal operation circuit. And you can see the flash circuit is always on. That's what this guy is doing. It's bouncing back and forth, it's flashing. So if we put the intersection into flash, the lights will flash by itself. And then this main bus relay right here is going to be what disconnects the normal operation from the flash circuit and vice versa. So it will also then swap over to, it will drop out, and normal operations will drop out when the flash circuit's on, and you know, same vice versa. So whenever it's closed, you have normal operation. Whenever it's open, you have the flashing operation going on. And you can see we have voltage running through it right now. It's all in normal operation. It's working like it should. But when we put the intersection into flash, it drops out the normal operation, and it allows the flash circuit to take over the traffic lights out in the field. And that's what's going to create that flash that you typically see when there's issues at a traffic light and all the lights are out there flashing by themselves. And this is typically what you'll have that goes bad when you see the intersections flashing, but you also still have green lights on, or the intersection cycling and still working like it should, but the lights are flashing out in the field. That means that main bus relay is not disconnecting from the field. It's having an issue, and it's allowing the normal operation to continue working while the flash operation is on. So that's the 2 main circuits that we have. If you don't consider everything out in the field to be a circuit, because that's circuitry as well, but we call those phases out here, and given the approaches on a traffic intersection, we consider those phases, not circuits. So we have 2 circuits, a normal operation and a flash operation here at these traffic intersections. And to kind of show that on the plans, but this is where it can get a little more confusing, you can see where the pins on this flasher unit here, you can see where the pins are going to jump over and it's going to work over to this power distribution. You got to have 2 sets of plans out now for this, because this is our power distribution block, which is this entire guy right here. And you'll see where it separates on that relay and jumps over to the flashing operation, or the flashing circuit, versus the normal operation, and how that swaps over. With our power distribution, we got our 2 separate circuits, the flash and the normal operation, and we have 2 separate plans here. That's how you could also, or how you'll trace down all your pins. There's more sets. We got another set, but this is going to be for detector panels and different devices inside the actual cabinet itself. This is going to be backboard, power distribution over here, and that's where those 2 circuits are. That's going to separate the normal operation and the flash, and you can see where it lays out all the pins and where they're going. And then I'm going to try to move this one out the way. It's less needed on the power distribution, but you'll see on the flashing side of everything, it ties back in to all of the load cells, meaning it can distribute power to all of the load cells. When normal operation has a failure or an issue, it transfers over to that flashing mode, and that's how it can feed back into all the signal heads in the field. But it will disconnect everything from the load switch. It's supposed to, at least, if the main bus relay, if everything's working, it will disconnect the normal operation, which is everything on the top side here, away from the flashing side. That will all be disconnected, and then you should only have power coming from the flashing circuit to the signal heads out in the field. Those are the biggest things out here on the traffic signal world. The next step's going to be wiring up field cables. Let's get into that. Hey guys, real quick, I want to talk about Ridge. Yes, the company that makes Ridge Wallet, they now make wedding rings, and I'm telling you, they look great. And it also comes with a silicone one, so you can wear it to work and it's not going to create a hazard for you. And right now we can get 10% off on these rings, or even their wallets, if you use the code YouTube10. So check it out and get you one, and never lose a wedding ring again, because if you do, they'll send you a brand new one and they guarantee it. Let's get right back into it. I'm gonna keep this set of plans out because that's gonna tie in a lot with this set of plans, and it's gonna help explain stuff. Again, gonna try my best to dumb it down and make it make sense to everybody. So I've gone over the flash circuit and explained that. Let's go over the normal operation. Yes, we've gone over the pin connectors, how it's tied into the backboard, using low voltage or ground that communicates in between to show outputs. Now it's field cables to the signal heads themselves. That's our job, to be pulling all these cables and getting it landed. And this is where certifications like IMSA or on-the-job training and being a proper tech and having a understanding of circuitry. Again, we don't like to call it circuitry because it's phases out in the field, but it's pretty much just circuits that's running and powering each individual LEDs out there in the field. You have to have a good understanding of what you're doing, because nothing in this cabinet can understand what these colors of the conductor is. It's just electricity. The controller, the conflict monitor, is not going to know whether it's a green cable that's powering that LED or this red one that's powering a separate LED. So if I move these 2 cables around, if I put this red from phase 4 on 4 green and put 4 green on 4 red, I'll kill somebody. That end of the day, you will kill somebody doing that, because nothing can catch that in this cabinet, because it's just showing that it is sending proper voltage and that the lights are working like they should be working to the brains of the intersection. That's how it would understand it, because it's copper at that point that's swapped up. So you have to have a good knowledge of what you're doing, because if you leave field cables swapped up, if you change up stuff like that, it will not catch a conflict, and you will have 2 green lights on that are conflicting phases, and you will be responsible for killing somebody at that point. And that's why there's schooling. Not a lot of schooling, a lot of it's going to be on the job training, but there's certifications like IMSA that can give people a more understanding, and that's why certain states even require you to be IMS certified, and even a level 2 tech or higher to even be doing anything inside the cabinet, and a level 1 tech to do anything inside of the field. Again, that's how these cables work. It just goes straight from the signal head, and then we have our neutral block back here, because you have to have a return source of power but these, like one green right here, that cable is going to run all the way over, and you can look at the phases in this diagram here. Phase 1 is this left turn lane out here. That flashing yellow arrow, that one signal here, it may be hard to see on video, but the green on that signal head itself is coming from this green cable going all the way for phase 1. Now the flashing light on it and the yellow and the red, that's technically an overlap. That is being overlap 13, or overlap A, excuse me. And the red, the black we're using for the solid yellow, and the orange for the flashing yellow, because technically, as its knowledge, everything in here, you can even see on the monitor, that flashing yellow, technically to it is a green, so you have to have permissive phases and everything together, and that's what the overlap is for. That flashing green is the overlap itself, same with the red and the yellow, and then the green is the phase. I know that's kind of hard to understand, kind of hard to explain a little bit too, but it's an overlap side, which is what that flashing yellow is, versus the green, which is phase 1 itself. So, and we correspond all of our phases together. So we'll use phases 2, 4, 6, and 8 as through lane traffic at these intersections. And most of the time, 2 and 6 are going to be our more popular or more busy highways. You'll have phase 2 and 6. And with 2, we use 5 for the left turn lanes on it. For 6, we use phase 1 for the left turn lane. And then 4 and 8 will be the through lane advancements on the side streets like you see here. Here at this cabinet, we can look right in front of the cabinet. These lanes here is phase 4. There'll be phase 8. I'm pretty sure this is not split phased out here. I'm wrong, it is split phased. Oh, I know why too. They're using overlap B for these right turn arrows. I recall, I mean, I did this work out here, so I'm just trying to kick back and remember all of that. But we are using overlap B for the right turn arrows, because there's plenty of times where these through lane traffics, or when they're getting left turns, that right turn should be activated as well, and just clears up a lot of these people coming out from the highway there. Sorry, gonna almost be ranting onto here, but I'll get distracted as I'm explaining and then try to go into more detail. So I'm trying to think of where we were at right there. Yeah, phases out in the field, 2, 4, 6, and 8, through lane movement. 2 and 5 goes together. 5 is going to be the left turn movement. 6 and 1 goes together. 1 is going to be the left turn movement. 8 and 3 go together. 3 is going to be the left turn movement. 4 and 7 together, and 7 is going to be the left turn movement. Now, since we just brought up split phase, let me explain that real quick. It is easier inside the cabinet, and it is easier to not mess it up later on or have any, because you can do it 2 ways, more than 2 ways actually. You can do it inside of the controller. You can change the ring timers, the ring structure, and you could split phase the entire operation in the controller, or even through sequences, you can change it all up and split phase it to not allow 4 and 8 to come on together. There's many reasons for it, whether we have too much traffic on each lanes, so that you want to separate the phases so they are both a lot safer. It allows each phase and approach to clear out by themselves and then goes to the next one, but it creates a less efficient intersection. So you always got to pick that safety or efficiency, and then you got to find that good middle ground in between both. And when you split phase, you make it a lot more safe, but you take away the efficiency of it, and that's where traffic studies all come together. But when you split phase, we'll typically bring over, because it's the easiest route, and for future techs or anybody else working on it, it doesn't take an engineer to come out here and figure it out at that point. You can come out here and just understand your cables have been moved around. We would now be using 3 and 4 as our through lane traffic. It will just be the approach there that will get a green, and then separately this approach will get a green, and then they can do their left turn, straight, right turn, whatever, but they'll have a clear, no conflicts with each other, which you wouldn't when they have all the same phase But people like to try to make that left-hand turn when they have a solid green ball and not a green arrow. That's what typically happens a lot when you split phase it. It dedicates each approach their own amount of time to have a green. I'm gonna feel like I'm rambling a little bit, but I'll keep on going with it. So that's how you'd see split phase setup. That's how it is right now. You see how they have the green light? That blue car that's coming up, he already missed the light, but he has a red light up on these two signal heads here and will not get the green if these lanes are green as well. That's split phase. All right, so now that y'all have a little bit more of an understanding of vehicle phases and approaches at an intersection, that's where, and we have discussed where these copper cables go to each LEDs. And yes, when you have a certain phase, like phase 2, we'll have one cable or one multi-conductor cable going all the way up that pole and then jumping out, going to that first signal head, and then pretty much splices back into the signal head itself, jumps out to the next one, and splices back in, and then jumps out again to the very last one on the arm. That's how we wire up the mast arms around here. They don't all have a dedicated cable, but they have a multi-conductor cable going to it, and they jump and splice together, and that's how we get power to all of the LEDs. So when this controller says, hey, we need to change lights around, comes down to these load cells, and it will start going from red to green and from green to yellow to red, and that is when you will have supplied voltage on all of these pins here, and that's what will power the lights in the field themselves. Let's get into vehicle detection. All right, so we have multiple forms of vehicle detection. This cabinet here is running an Iteris device at CCU. This is the video cameras out in the field that are sensors that will pick up vehicle presence and then communicate back to the controller and lock in these vehicle calls right here that was saying, hey, this vehicle is present at the stop bar and they need a call for a green light. And you can see that is how it is switching over to the next phase, which it is them, and they have the green light now and they are free to clear. And as they come off of that approach, you can see that that call just dropped and it no longer is needed for a green light. As vehicles come in, and if they hit it, and if they time it and it gets hit right, then it will then give them a little bit more time so they can clear through the intersection. If they're too far behind and the cycle's already started, then they will miss the light, and that's why you get held up at a red light. When you're with a group of vehicles, you're more guaranteed to keep the green lights. When you're separated from a group of vehicles, you have the higher chance of catching a lot of red lights. So in short term of that, all these Cat 5s, these ones here are going to those cameras that are up on the mast arms. You can kind of see them up there. These are directly going from this lightning arrestor all the way out into pool boxes and up to the cameras, and then it comes out of this lightning arrestor and connects into the CCU itself. Then we program the cameras, set it up for which phases are which on the cameras itself, and then this communicates through an SDLC cable. It's going into a hub that communicates into the traffic signal controller, and to just show the whole thing being actually enabled, you can go into unit data, go into the port 1 ITS data number 7, and you can already see where all these BIUs you can start enabling for different things. But as you come down, BIU number 8, that's the number 1 detection BIU for TS2. That is the one we enable. That's the BIU that this CCU itself is operating under and communicating to the controller with. So now we have a good understanding that's operating under BIU and it's communicating to the controller itself. These detectors are recognizing all of that, recognizing what's in the field, and communicating to the controller itself, allowing vehicle calls, and that is how people are going to get green lights. Now, that is more recent setups. Let's go back to inductive loops, and that's where I can show you on paper how that works. This entire side of the cabinet is our detector panel, not an entire thing, but pretty much from here over is our detector panel for inductive loops. We have some other inputs right here also if we were doing different things at this intersection, different, whether video cameras, however. So these these are all running, this cable that's running from all these 4 blocks here, jumping over, coming up, and they're going into the back side of this card rack. And when we have power connected and amplifiers inside of this card rack, that is what's going to send signals back down, or from these cables, come up into it, and then back out of the card rack, and it's going to hit pin connectors or pins on this side of the panel. We can actually show you some. So you can see the block is like phase 5 vehicle detection, and that's going to show which block and everything. So you got the Q block, Q2, and it's really, they should be jumped together, which they are. Q1 and 2 are jumped together, and that's going to be for vehicle phase 5 vehicle detector. So that's going to come out of the card rack. Again, this going to the card rack, and then out of the card rack to the vehicle detector, and then from the vehicle detector to the backboard on the proper pin, and then that is connecting to these pin connectors and back into the controller, which will then lock in the call. And then you'll have calls just like this iTerrors device is. That's a little bit more software. This is 100% hardware that's showing all of this coming up, and it'll give them a call when that amplifier shows that there's a vehicle present, and it will put in a call through those cables that are jumping all the way into the pin connector and to the proper pins of this controller. And that is what will be used. It'll be a ground that will lock in calls, and they'll get a green light sitting on the approach, and that's how an inductive loop works on the cabinet side of the inductive loop, not necessarily in the field. In the field, it's a little bit different, but it wires up to the panel itself, and we'll cut that in the asphalt. You have the inductive loop, comes back and works the same as these cameras, but it's all a hardwired cable that connects all the way back into the controller. That's going to put in a ground or a logic that's going to give that call, instead of cameras and software saying, hey, I got a vehicle present, put in a call please. It's going to just use pin connectors to make all that work. All right, let's get into something like pedestrian detection devices. Out here at this intersection, we recently upgraded them to a Polera push-to-talk CCU and pedestrian buttons out there in the field. So almost the same, or it is about the same as this card rack. This CCU is hardwired directly to the detector panel and to the backboard, and even the field lights themselves. I say field lights, it's going to be our pedestrian phases out here. Out here we're only using pedestrian phase 2, which is going to land on 9. You got the red and green here. That's going to be the don't walk and the walk indication, and all that's going to be hardwired and pinned back into the CCU itself. And then the push button itself is going to come to this PLC board. The push button is connected by these 2 cables, and this is coming back into the controller of it, the CCU. And so when somebody presses that button and these 2 ground out, it's going to send that signal, come around and into the controller. And then from here, this is hardwired into pins on the backboard, and pins, a couple different pins. It's really on this side here, but then it jumps over to the backboard. Pretty much the same way I just explained the amplifier in the card rack. That's how this is wired up too, and then goes into the pins of the controller. And I can show you. So right here, connector A and pin, what does it say? Pin G and pin H, or H and J. Could have that a little backwards right here. But those are the pins on the backboard itself that are going back into that controller, and that's going to be the pedestrian clear and the pedestrian walk and the don't walk. And that's how all of those are activated. I guess all 3 of those. Let me look real quick. Yeah, you got G, H, and J, I believe. And that shows you where they lay out on the backboard itself. You can see how they jump over to A29, A32, and A35. Look on the backboard, A up here, and you got don't walk, phase 2 don't walk. What did I say on the other one? 32. So you got 29, that's going to be the don't walk. and then you got 32 that's going to be the clear, and then you got 35 that's going to be the walk. And you can see that those are jumped off, and that will even show on the backboard sheet itself why those are jumped off. And that is to monitor, typically that is going to be have a jumper on there, so then it can also connect into the conflict monitor, and that will be monitored as well. So if you're still with me, I hope you're enjoying the video, and as always, make sure to hit the like button. Let's keep looking into some stuff. We can look into the Opticom system now. So inside of this cabinet, we do have Opticoms out in the field. They are not hooked up or wired up just yet, because this is a new cabinet. This device got transferred from an older cabinet. It's been rewired. This D harness is what activates all the preemptions at an intersection, and Opticoms are a preemption system. It's going to be used for emergency vehicles, so as they need a green light and they can come up with their strobe light, flash that little birdie out there. It may be easier to see on this pole, but they'll flash that birdie with it, and it will send a signal all the way back to this receiver, and then this will output almost just like the card rack system. Again, we use TS1 for pretty much everything out here in Mississippi, and it's all going to be the same. It's going to come from the device, from a signal, come connect back to the amplifier, jump off of the amplifier, connect into the side panel, or really this D harness here. This D harness is going to be jumped to pin connectors that are in the controller itself, and into this D harness connector as well. And when one is activated, that is how they will get that preemption call that will lock up the intersection and continuously give them a green light until they clear through the green light. And then it can be set up in the controller of how long does that preemption need to last after it's cleared, and which phases need to dwell, which ones need to stay activated, and what needs to happen. Sometimes, you know, different preemptions will do different things. If you got railroad systems, you can either have a preemption that's going to work as they'll activate a no left and a no right hand turn, or sometimes you'll even have a flashing circuit that will connect to it, and it will make the intersection go into flash when you have a train coming through, and kind of lock up the entire intersection at that point. So different preemptions do different things. In these cabinets, that's all ran through the D harness, jumps over and connects into the controller itself, and then the controller is programmed and set up for those preemptions. Once it receives the signal, it can output and do the proper vehicle phases, what needs to go green and stay activated, or put the whole intersection into flash. That controller will output that, and then you'll have either here for Opticoms, it's real simple because the controller just outputs to the field lights and everything stays the same, and the controller will just be timed on it. When you have like those no left hand or right hand turns, I'd have to go all the way to like Pascagoula. I know where some are that we installed that I can show y'all. But when those are activated, you'd have a relay block and everything you'd put up inside the cabinet. So that relay, it'll get that signal, it'll know that relay will click on, and it will lock up in the controller to make sure certain phases can't go green anymore, and then it will activate those particular preemption devices out in the field. Like a big, they don't look big, but they're pretty big when you're installing them. It's a big aluminum box, and it has a LED faceplate showing like a no right hand turn, and the reason RA like yield to a pedestrian on right turn because the pedestrians are activated. Pedestrians even have preemptions that can be used. The list goes on and on. You can pretty much do anything and everything that you can think of and dream up for traffic lights. You can make that happen. It just starts costing a lot more money when you do so, but you know, safety, there's no expense to safety, so it's worth it at the end of the day. So inside of these cabinets, what you've learned today, it's a lot of old school, and people will say this is dinosaur technology, but it's technology that has worked for decades upon decades before all of our times at this point. Some of y'all are old, so maybe not before everybody's times, but pretty much before majority of our times, and it has been working, been reliable, tried and true for generations, And that's why you still see a lot of this happening in big areas or everyday states. Don't want to move away from this because, as we said, once we start getting into these SDLC cables, and once we get into, I'm gonna go back to it in the unit data and the port 1 stuff, we can just, I'm gonna go up real quick. 254, that's how many you can do, BIUs you can run on this controller at a given time. And the moment you start using more and more of these BIUs, the more issues you can have at an intersection because of a cable. Let's say an SDLC cable goes bad, or it's just not plugged in all the way. That can create issues, or they just get vibrated loose. Same with it, these nuts or these bolts right here on the backboard, they can be vibrated loose and back out a little bit, causing issues as well. But you'll typically see these pin connectors right here, these SDLC cables, if they short out, you'll have a lot more issues. When the backboard, if it shorts out, you're typically still good to go. And yes, can create issues, but typically still good to go when, as long as your cables and everything on your backboard is still good and nothing else is grounding out anymore, and you fix that issue, it's back up and running real quick and doesn't cost any money. Versus when these cables go bad, the cable itself is like 80 bucks, plus the controller will go bad, the CCU could go bad on the ports on the conflict monitor could go bad. With TS2 cabinets, you'll see load cells will have SDLC cables running to them. Those ports could go bad. Everything in the cabinet itself will have an SDLC cable running and communicating through those BIUs, that 256 different BIUs. So a lot you can do, 254 BIUs, a lot you can use, but the more you do, the more issues you're typically going to have with that. Where this backboard and these cabinets here, I'll tell you right now, they're just about indestructible. And when you do have issues between stuff, it's usually changing out like a main bus relay, or it's changing something out in the power distribution, or you're just having a short or grounding out on one of these connectors, one of these pins, and you can easily resolve that versus spending $4,000 on a new controller because you blew out the port inside or on the SDLC port 1 on these controllers, or your detection devices. So that's why you're not seeing a lot of the upgrades, or at least for here, why we're not seeing a lot of the upgrades. And I still believe in them. I like the TS1 options. One, I think it picks my brain a little bit more than just plugging in the cable and activating and enabling a BIU and setting it up. This picks my brain a lot more whenever I get to pull out the plans. You feel real smart when you're tracing down stuff and you figure it all out, and you figure out that a pin's grounding out or something different like that, and you can fix that and resolve it. I enjoy that a lot. And again, it's just tried and true. And when we're looking at trying to have low maintenance, efficient intersections, and yes, once you do more TS2 options and stuff like that and run things off of BIUs, you can start getting into a lot more efficient intersections and adding a lot more things and easily adding in extra things at intersections, versus when we gotta have to add in majority of anything. It can be a lot of add-ins to these cabinets, depending on what we have to add into. Like if those preemption devices we were talking about earlier, if we had to add one in, we have to add in the whole panel. We have to trace down every pin and cable, hook it all up, instead of just plugging in a cable. So it's more work to it. But again, I like it a lot more. It's tried and true, works, maybe dinosaur technology, but you can't beat it. And for all the people that are out there that are like, oh, you can do this with a Raspberry Pi. Yeah, software can change out some lights, but you'll kill somebody. At the end of the day, that is what 100% of me is trying to avoid, is trying not to kill anybody. And when you start messing around with stuff that you don't know what you're messing around with out here, you will have issues. And a Raspberry Pi, if you got struck one time, or even just dealing with these weather conditions that these typically deal with, again, lightning will strike. These can a lot of this stuff out here in the field can take a direct hit and have no issues. something like a Raspberry Pi. Again, it's not even a good conversation of it, but lightning would strike, and then you will have a mess of issues. You'd have lights just going crazy at the field. Yes, things can happen here. If you lose the neutral, stuff goes crazy. But typically, but it's not a software and it's not a controller issue that's ever going to create or present those kind of issues like you would with a substandard open source device. So why it's set up how it is, and why I don't even think it costs that much money. I know how much it costs. It doesn't cost that much money compared to what a lot of people probably think it costs, but we're looking to keep everybody safe, and we're looking to have nobody killed while driving through these intersections. And when you have reliable technology, that's what's worth everything to it. And this is the same kind of equipment that you would see NASA use, that you would see military operations use, and it's a reason why they haven't upgraded and went to open source devices. There's a reason why they haven't gone that route yet, because when they're putting their people in spacecrafts, sending them up in the air and everything, they're trying to not kill those guys that they're sending up there. And the same thing we're doing here, we're trying not to kill anybody on the roadways. So dinosaur technology, but it works, it's tried and true, and we'll use it over and over again because it is the better option to run, in my opinion. Yes, I love the future. I want to see the upgrades. I want all that stuff, but I want it to be tested and used for 10 years until it's rolled out into the field too, and see everything works. Or just, you got to pick the right areas for everything like that. And for how it is in Mississippi, this is pretty much what you're gonna get, and tried and true. Again, I can't say it over and over again, it just works. And how we've explained everything, I'm sure I've ranted and rambled a lot, but it's just pin connectors that come down and connect to amplifiers between our detector panel, our PLC board, and our ICCU here, or even a BIU that's running from our conflict monitor, our CCU for our Iteris devices that's connecting into the controller and sending in specific inputs to it so that this controller can output properly. That's what you're gonna see. This is not as vital as the operation of the controller and what's working out in the field. So I do 100% agree with upgrading this stuff to TS2 options, and that's why I really do like the TS1 hybrid stuff that we do. Yes, it's annoying because we typically see more issues out of them, but it is also a lot better because you can do a lot more advancements with what you're wanting to make the advancements with. Traffic lights are going to change from green to yellow to red, and from red to green over and over again. There is zero reason to try to run that through software over just hardwiring it all and knowing something's going to work. All right, guys, it's starting to rain a little bit here, so I'm gonna go ahead and about to be leaving out of this intersection. But look, making this video to try to give the general person a basic understanding of what's going on in one of these traffic signal controller cabinets. I know it was probably still confusing, and for your terminology freaks out there, please go ahead and critique me in the comments. It helps out the videos, and heck, maybe I'll even learn something out of it. I'm still always available to learn. Love learning more. I'm never gonna say that. I know everything about these systems. I know a lot because it's my job and it's what I do for a living, but I do also love sharing that with people, and obviously I had to learn it somehow myself. So if you enjoyed this video, don't forget to hit the like button, and you know, as always, thanks for watching. Peace, guys.